Okay, let's get going. Good to have you here. Okay, we are down to the last and hardest and greatest piece of this course. I think today will actually be the last lecture. Okay, everyone's happy, but I'm gonna have to drag you next week as well because we need to do some activities and talk about the exam. But then next Thursday, I do not anticipate that you have to come so that you can spend time on your other courses and study for this course, for this exam as well, okay? But as long as you promise me that next week, next Tuesday, you all try to come into class. I'd rather if you're here in person, but if not, that's also fine, okay? And this lecture is kind of the hardest. And like if you've learned anything in this class, this is the lecture where you can show it off, because it is going to combine pretty much everything, okay? And if you remember last time, we were talking about these boundary value ODEs. And I proposed to solve them using the finite difference method, because other methods, although they exist in the literature, they're not as flexible and generic as the finite difference method. The flip side of applying the finite difference to a boundary value problem is that you have to do it on a problem by problem basis. If you change your boundary conditions a little bit, you're going to have your matrix structure is going to change. And the idea was you would convert, you would take the continuous differential equation, apply a finite difference approximation to the derivatives, and whatever derivatives you have in that equation, you might have a second and a first derivative. I mean, the possibilities are unlimited, really. But you just apply the finite differences, derive an equation at every point, which is a linear algebraic equation relating the unknowns. In this case, we're talking about temperature, Ti, Ti plus 1, Ti minus 1. And then you build a system of linear equations and solve it, right? And we looked at both Dirichlet and Newman boundary conditions. You can combine those on the left point, on the right boundary, both Newman, both Dirichlet, any combination of those. And so there's unlimited possibilities, but the technique should be applicable to any problem. So if I were to add a first derivative to this problem, to the problem we solved last time, you just apply a central difference on that first derivative, and it just adds one more coefficient to Ti plus 1 or Ti minus 1, right? So it's just a matter of trusting the methodology and applying it on a problem per problem basis, okay? But today I want to present you with the same problem, but with a right-hand side that is a little bit more complicated than the problem we solved last time. So the problem we solved last time had essentially just the temperature on the right-hand side, Ht minus T infinity. Now I have alpha T to the power 4 minus T infinity to the power 4, okay? So same procedure, there's a boundary value problem. It has two boundary conditions, T0 equal fixed T left, TL fixed at T right. Could be a Newman, doesn't matter. The same technique applies, but the challenge here is to take this equation now and apply the technology or the methodology that we developed last time. So that's going to be your next few minutes. I recommend you work in groups and take your time. So I want you to discretize this equation. Sorry, this should be a second derivative here to remind you of the finite difference formula, d2 phi by dx squared. Okay, so up there is your reminder of what d2 phi by dx squared is, a second order approximation of the second derivative. So go ahead and apply that, okay, at an arbitrary point I. Don't worry about the boundaries. Don't worry about nothing. Just take that discrete equation, discretize it, and apply it at a point I, and then attempt to come up with a system of equations to solve for the points, for the values T1, T2, T3, you know, T2, T3, T4, all the way to the end, okay? Last time we had a system of linear equations. So now I want to know what you get, and I want you to explain to me, Kana, how you would go about and solve it, okay? Kimball and Jake, do you want to work together? Okay. So Lizzie and Brooke, if you want to work together, want to work with Rich, just try to get some collaborative effort so that you don't have to do it on the exam. So once you think you obtain a system that you want to solve, I want you to also describe how you would go about and solve it. Okay, just using words. Mm-hmm. Yeah, this is the last lecture. Why? Okay, so we might finish a little earlier. What time do you want to leave?
Just soon enough.
Okay, that's okay. I'm not worried about you, Maxime. So. There's no trick question. There's no magic that you have to do. Just apply the discretization, see what you get, and then remember we studied something like this before, okay? So once you have the generic formula for point I, you can apply it at all points, at T1, at T2, at all the interior points, right? T2, T3. And you know that should give you enough equations for all the unknowns that you need, right? Just like we did with the other problem. But there's something different about this problem. Mm-hmm. I heard an over there. So here's my suggestion. First, write the generic formula at point I. Apply the discretization, expand everything, all the terms, put them on the left-hand side, the right-hand side. It really doesn't matter, okay? And then apply that discretization at T1, T2, at T2, you know, because you know T1, apply it at T2 and then T3 and then dot, 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 and then at Tn minus 1. Okay, so you have as many equations as there are unknowns, right? So you'd have whatever, n minus 2 equations and n minus 1 unknowns. But then, okay, what kind of system of equations is this? Can you separate it? Can you separate it into, can you separate the unknowns from the coefficients or not? That's what you need to get to, right? So that's what you need to see. So Ethan, you said something correct there. Yeah. Yeah, so write it down. Yeah, so what do we do for nonlinear? So take the next step. what do we do when we are faced with a nonlinear equation or nonlinear system? That's where that other chapter comes in. Well, what does this even make sense? Yeah, so so this is not a coefficient, right? Because it depends on t itself. But you're onto something which we will describe later. But that's not the step that you just have a nonlinear system of equations, right? But you can't separate it that way, right? Pardon me? Well, you can do whatever you want, but it doesn't necessarily make sense. All right, so let's see. Who thinks has, let's see what kind of solutions we got. Matt is pointing at Kevin, Kevin pointing at Ethan, Ethan is pointing at Evan. Do we have anything in this column? No? Well, you said something. You're not done yet, I see. Okay, so let's see this column. So you discretize it, right? So you get, you know, ti plus 1 minus 2 ti plus ti minus 1 over delta x squared equal alpha ti to the power 4 minus t alpha to the power 4, right? So we all got that. So what's the problem with that equation? You take it, apply it at point 2, at all the interior points, all the way to n minus 1. You get one equation at point 2, one equation at point 3. So as many equations as there are unknowns. So then what do you do next? Can you just solve it? Can we just write it as ax equal b? Why not? That's correct. We cannot write it as ax equal b. In other words, we cannot write it as a linear system of equations. Why?
Because right now you have your ti on the right-hand side, or at least some layer.
Ti to the 4. Yeah, ti to the 4th, right? I mean, if you had ti, you would move it to the left-hand side. But suppose you had sine of ti or cosine of ti or ti to the 4. That's a nonlinear equation, right? We spent like 4 or 5 lectures on that. At every point, you have a nonlinear equation. And you cannot just the same way you cannot solve a nonlinear equation by a simple algebraic manipulation. When you have a system of nonlinear equations, you cannot solve that as a system of linear equations because it's not. It's a system of nonlinear equations, right? So that's the critical difference here between this problem and the previous problem. The issue is not that you have ti on the right-hand side. We had ti on the right-hand side in the previous problem, but it was just that, ti. Right now, the right-hand side, ti shows up non-linearly. So you cannot separate it. What do? You put ti cubed times ti, but ti cubed is not a constant coefficient, right? It's going to change at every point, right? And so this is a system of nonlinear equations, right? And how do we solve systems of nonlinear equations? We build the residual function, we do the Jacobian, we linearize it, right? So same thing that we did with nonlinear systems of equations, okay? So let me show you the math. This, I suppose everyone got this. So you just write it down, just apply the discretization technique, but then you have to make a judgment. Like when you look at this equation, you go ahead and if you try to go ahead and apply it at each point to build a system of equations where it's not a linear system of equations, it's a nonlinear system of equations, right? And so what you would have to do is define actually the residual function. Okay, if you were to define the residual function at every point I, you move everything to the left-hand side or everything to the right-hand side, whatever you like, it doesn't matter. But I know how much you hate systems of nonlinear equations, okay, based on your feedback on the muddy points. So we're not going to take that route because it would be insane, not according to the formal definition of insanity, which is like repeating the same thing and expecting a different outcome. But it would be insane or impractical or incorrect to, not incorrect. it would be impractical or inefficient to solve such a large system of nonlinear equations just using this brute force approach that we learned last time. Why? In these problems, you typically are going to have hundreds of thousands of points, okay? Even millions of equations. So yeah, I'm giving you an example here for an ODE, but this typically happens when you have three-dimensional partial differential equations. And you can imagine you get the curse of dimensionality there. If you have 100 points in each direction, that's 100 cube points, right? It's crazy. You get, you know, millions of equations, okay? And solving a system of a million nonlinear equations is very, very hard to do. So instead, there's a different methodology that essentially embeds the nonlinear solve, Newton's method for systems of equations. We kind of embed it directly into this differential equation. So you're still almost applying Newton's method, but you're not kind of doing it as a separate step. You're actually building it as part of the discretization process, okay? And this is called source term linearization. So this kind of problem that I just showed you, you will be able to spot it immediately when you look at the right-hand side of the governing equation. And if the right-hand side has nonlinear terms in the dependent variable, okay, then it's a nonlinear, it's going to result in a nonlinear system of equations immediately. Okay, so you should be able to spot that just by looking at the ODE. So if I give you a question in the exam saying, hey, is this ODE going to result in a linear or nonlinear system of equations? You should be able to spot that just by looking at the right-hand side. Okay, without doing any fancy thing. We're not doing any, there's no tricks here. Okay. Now, to solve this issue, we follow a procedure called source term linearization, which essentially is a way to embed Newton's method, the Jacobian and all of that. Instead of doing all of that very annoying stuff, we're just going to embed Newton's method in the discretization process. So let me show you how it works. On the left-hand side, I'm going to show you the generic formula of source term linearization. And on the right-hand side, I'm going to show you how it applies to our particular problem. Okay? So we start with a generic differential equation. Okay, this is a boundary value problem that's kind of implicitly assumed. Okay, with the right-hand side function called f, or we can call it r sometimes. That's a function of both dependent and independent variables. We're going to assume in general that this f is nonlinear. Okay, nonlinear in u. Doesn't matter if it's nonlinear in x because x is a known quantity, right? It's an independent variable. But u is what matters. So if you have u cubed, sine u, sine cosine u, log u, whatever, okay, those are all nonlinear. Okay. For our problem, we had d2t by dx squared equal alpha t to the 4 minus t infinity to the 4. T infinity to the 4 is not, it's a non-issue. It's a constant, but it's t to the 4. That's the problem. That's the issue. And in this case, our ODE example, the right-hand side is only a function of t, of the dependent variable, temperature, not x, and that's f of t. Okay, so follow this very, very clearly. Okay, so the idea would be, okay, we're gonna start with a guess solution for u. So remember, with nonlinear solvers, with nonlinear equations, we kind of always started from a guess and refine the guess. Okay, so here we're gonna do the same thing. Despite the fact that this is an ODE, you know how to convert an ODE to a system of equations, linear or nonlinear. So we're going to assume that, okay, we're going to do that. And our answer is going to be something. We're going to start it off with a guess. We're going to call that u star. Okay, so you kind of know u star. You know it. It's your initial guess. You're starting from u star. So the initial value of u star is a known value that you supply to the system, to the solver, to whatever function and routine you have. Okay. In that other example, we call our guess solution t star. Now, here's where the magic comes in. And again, this is another version of the Newton solver that we developed for nonlinear equations. We're going to go ahead and do a Taylor series of the source term, the entire source term, the entire right-hand side. Okay. We're going to do a Taylor series around U star. So we're going to fix X. Okay. We don't care about X, but we're going to do a Taylor series around U star. That Taylor series looks like fxu equal fx u star, right? So we're expanding around U star plus U minus U star, the distance between U. Remember when we did Taylor series in X, you had X minus X0, or you had f of X0 plus X minus X0 df by dx. Same thing here, you do f of X U star plus U minus U star times df by du. Now this is where the Jacobian is. The df by du, that's the Jacobian, right? It's the derivative with respect to the dependent variables, right? So that's where your Jacobian is coming in, really. Okay, but we're kind of doing it in a much simpler way. Okay, it's not going to be as complicated as the other technique we used. Now I know for Newton's method, I'm going to truncate here, so I put 3 dots over there, right? For our problem, this is simply f of t equal f of t star plus t minus t star df by dt evaluated at t star. Be careful here. You have to evaluate the derivative with respect to u or t at U star or T star. Now U star or T star, we're going to start with a guess for those, and then we're going to improve that guess. Okay, so we're going to keep iterating that guess until U star and U are equal. That's our objective. That's how we're going to find the solution. Okay, so we're going to truncate at first order, like I just said. The other one is already truncated at first order. So in this case, we have f of xu, f of xu star, etc. So now go ahead and apply this truncated formula to this problem. So your right-hand side here is alpha t to the 4 minus t infinity. Assume you have t star. Go ahead and apply this to our right-hand side. Alpha t to the 4 minus t infinity to the 4. Go ahead and write it down. So apply this truncated Taylor series to the right-hand side for our problem, for our example problem. So in other words, your f of t is alpha t to the 4 minus t infinity to the 4. Good. Okay. So now can you see what happened? All the cubed quantities are kind of constant, right? Because you know what t star is, and you have only one unknown t.
Oh, right.
So kind of we linearized it, right? See what happened? But now we have to iterate. So I'll show you in a second. Okay, so now you see where kind of what you did earlier was kind of similar to this, but you're missing this for alpha t, right? So you see now all the cubed or to the power 4 terms, they're all on t star, which you know, right? So t star to the 4 is a constant, just like t infinity to the 4, just like t star cubed, right? So you only have t as the unknown on the right-hand side, which makes it linear. Okay, Correct. Good. Okay. All right. So what do you observe if you observe anything after you do that Taylor series expansion around T star? What happens to all the cubed, to all the terms that are to the power 4? What happens to T to the 4? Do you still see T to the power 4? No. What do you see instead? T star to the power 4 and T cubed, T star to the power 3. What happens to T? It's just T, right? It just shows up as a T, correct? You see that? Perfect. Yep, there's your T, right? So now remember, this is going to be done at every point I, okay? At every point I. Same thing, T star, we're going to have a T star I, a guess at every point, okay? So if this is your f of t, alpha t to the 4 minus alpha t infinity to the 4, then you get the first term, f of t star. You just simply substitute, put t star over here. So you get t star to the 4 minus t infinity to the 4, plus t minus t star times the derivative of the right-hand side with respect to t, which is 4 alpha t cubed, evaluated at t star. So you get 4 alpha t star cubed. Now, when you look at this new right-hand side, this is called a linearized right-hand side around t star. When you look at it, everything here is known except for t. Not t squared. There's no t squared. There's no t cubed. There are no nonlinear terms in t, which is exactly what we want now. So we've approximated the right-hand side to make it linear, so we can turn it into a system of equations, a system of linear equations, okay? But we still have an issue in that T star might be very far from the truth. So now we're going to have to rebuild that system of equations over and over again until we drive our guess to the true solution T. So we start with a guess T star. We take this, I'm kind of sketching what's going to come next. You start with a T star, you approximate the right-hand side with this, you plug it in, you solve for T. And then you see, is T far away from T star? Probably yes. So now use the new T as your T star and repeat. That's it. It's exactly what we did with nonlinear equations, except here we did just one extra step. We linearized the right-hand side. Now that's what we did with the residual function, if you think about it. That's kind of what we did with the residual function with nonlinear algebraic equations, except here we're applying it to the ODE. Okay, so when you have this now, you substitute back into the ODE. And again, on the left-hand side, I'm showing the generic form for an arbitrary f. So you can take this as your general notes, okay? If you're in doubt, derive it again, but you can take this as the general formula for this case. For this particular problem, this is what you have, d2t by dx squared equal all of that, okay? So now you discretize. For example, for a central discretization for the second derivative, at any point I, this is what you get. So now you're going to have a t star at point I, a guess at every grid point, because you have a nonlinear equation at every grid point, which is now linearized at every grid point I. But the great thing about this is that now all quantities show up, all unknown quantities show up linearly. And the unknown quantities are the ti, I minus 1, and I plus 1, right? They all show up linearly. T infinity to the 4 and ti star cubed, etc. They're all known values. They're like constants, okay? And then you collect terms. On the left-hand side, it gets kind of really nasty when you do it in a general way. But on the right-hand side with this example, now you have a linear algebraic equation at every grid point, right? Where you have the unknowns on the left-hand side, which show up linearly, and known terms on the right-hand side. And now you can write this as a system of linear equations. So you build the linear system, and that on top here, I'm showing the generic formula, the generic system of equations for this. And you see I have question marks and the front row, at the top row and the bottom row, okay, because I don't know what the boundary conditions are, okay? So when you know the boundary conditions, then you can substitute. So if you have Dirichlet, you would have 1 and 0 and t left, and 0 and 1 t right, for example, if you have Dirichlet conditions. If you have Newman conditions, then you have to do the Newman procedure and approximate the derivative and all of that. Okay, it gets a little bit, you'll have kind of non-trivial terms, but you just apply the same strategy we did before. Okay, for our specific problem with the heat transfer in the rod, this is what you get. We had Dirichlet conditions on the left and Dirichlet conditions on the right. Okay, and this is what you get. Okay, so we're not quite done yet. Okay, so there's a U star everywhere. There's a T star everywhere. Okay, and we know U star was only a guess to the true solution U. So when you have this equation, this system of equations with a given U star, and go back to the previous slide. So when you have this system of equations with a given T star, all of these quantities here are numerical values. They're known. You plug them in, and you solve for T1 all the way to all the way to the Tn, to the last point. Okay. But then you ask yourself, well, this is my solution T. How far is it from my guess? If it's far, very far, then my guess was really bad. So I have to improve now my guess. I'm going to use this new solution as the new T star, plug it back in here. You have the system of equations. It doesn't change, the system of equations. You put it back in here, you solve again, and you keep solving and solving until the solution T and T star no longer differ by whatever tolerance you want. Okay, it's identical to the idea of solving a nonlinear equation or a nonlinear system of equations. Okay, and linearizing it and starting with the guess and iterating until your solution and the guess are almost identical. Okay, right? So here's a pseudocode. Essentially, you guess the solution values ui star. So remember, there's a guess at every grid point. Okay, typically you choose all the guesses to be the same. For example, for the heat transfer problem, I'm going to assume the initial guess for the temperature is 300 degrees everywhere. Okay, my best guess, right? You can make it kind of look like a profile, but I don't think it's gonna help that much. Okay, you use those start values to update the coefficient matrix and the right-hand side because you have stars everywhere. Okay, update the left-hand side matrix and the right-hand side vector with these values. Then solve the system of equations for the unknown dependent variables, T1, T2, T3, all the way to Tn. Okay, and now ask yourself, is my new solution, how far is my new solution compared to the guess, not the initial guess, because you're improving kind of, right? So if you start with a guess, you get a solution, it's probably going to be very far. So you're going to have to repeat until you reach a certain tolerance. Okay, and then you stop iterating, just like we did with a single nonlinear equation. Okay, now you have to take the norm, right? Because you have a system of equations. At every grid point, for every equation, you're going to have a different error. So you need to take the norm of all of those. We do an L2 norm, L infinity, it doesn't matter. Okay. All right, so let's go ahead and do this in Python. Let me go back to the, okay. I kind of have everything repeated over here. All right, so grab a fresh Python notebook, please. So we can work on this together. So when I say like this is like, this brings everything together. We've been using linear systems in almost every chapter we touched upon, right? This last part brings in finite differencing, okay, linear systems and nonlinear equations, okay? It kind of brings the hardest pieces of this course together. feel free to get started. I'll move the slides to the over here. So feel free to get started. On this, let me grab. Bless you. Okay, let me just create a new notebook. Okay, got a new notebook over here. We're gonna need this guy on the side. Okay. I'll just swap back and forth. Okay, so I'm gonna bring in my boilerplate code here. Import NumPy. Well, I don't need ODE5, so go away. Okay, and then I don't need sci-fi. I don't think I need that. Okay. So okay, so we're just gonna hard code this. No use of kind of functions and fancy kind of right-hand sides, etc. We're just gonna do it for this particular problem. I'm gonna start by defining the number of points. Let's say 100 points. Number of grid points. Okay, can you guys see? On the way back. Okay. Okay. It's kind of strange they don't have a projector on this side. Okay. Our x0 is 0. That's kind of and L is 1. These are the extents of the rod, the domain. For this problem, we are solving D2 by, if I can get my slides. Okay, we are solving, my slides. Okay, we're solving this D2t by dx squared equal alpha t to the 4 minus t infinity to the 4. This alpha is just a heat transfer coefficient. Okay, so we're just gonna declare an alpha over here and just put it, 1 e to the minus 8, for example. Okay, this doesn't matter. This is just to illustrate the methodology. T left is 300, T right is 500. Okay, so Kelvin. Oops, Kelvins. Okay, and then T infinity, because this is a radiative environment, I'm gonna do like maybe 1,000 degrees. Okay, could be less. Yeah. So now to build this coefficient matrix, this is a tri-diagonal system of equations, right? We know how to do that. So we're going to build a lower diagonal, main diagonal, upper diagonal, and we're going to build the right-hand side. So we know how to do that. Okay. So let's go ahead and do it. For the lower diagonal, I have np dot ones of size n minus 1, right? For the lower diagonal, they're all ones except the last entry is 0. And LD minus 1 is 0. Okay. For the upper diagonal, I also have MP dot ones of size n minus 1. And the first entry for the upper diagonal is 0.0. Correct? Yep. The upper diagonal, it's all ones. Okay. Now, I don't have 5 points. I have n points over here, right? That's kind of the power of this. That's okay. And the main diagonal. Oh, look, it has a delta x in it. So what do we need? Let's create a lint space, okay, to get a delta x spacing. Okay. So let's go ahead and do a linspace, x equal mp dot linspace, linspace x, linspace the x0 to L with endpoints, and we're going to do dx is x1 minus x0. So that gives us, because dx is fixed, so that gives us our delta x. So now we can build the main diagonal. Okay. Oops. Okay, but there's another issue. T star. Thank you, Nick. Okay, so our main diagonal has T star in it. And we're going to start with an initial guess with T star, but we're going to have to keep iterating on this T star, right, until we drive it to be equal to T. So the creation of our main diagonal and the right-hand side, they have to be within an iterative loop. Agreed? Does that make sense now? Because if you do it just once, you're only solving for one iteration of the system. You're only solving, you start with a T star, you solve for T, and you stop. But if you wanted to do it again, you have to recreate this diagonal, right? Because it depends on T star, because T star is changing every time we are solving the system. A lot of faces squinting. I don't know if it's a good thing. Okay, so let me go ahead and do it, and then maybe we explain after the fact. So I need a T star. We need an initial guess. Okay, my initial guess is going to be a T is equal, let's say 300 times mp.1s of size n. Okay, and I'm gonna create an error maybe. I'm gonna create a tolerance, let's say of 1e to the minus 2. That's kind of how much tolerance I'm gonna tolerate, how much error I'm gonna tolerate. And then we're gonna initialize with an error that's very high. Okay, we did this before when we were doing iterative solvers. So while my error is greater than tolerance, okay, solve this system of equations over and over and over again. Okay, you can call this thing here T star if you want. Okay, so that you doesn't get too confusing. So now we create the main diagonal, which is D is equal to minus into 2 plus 4 alpha delta x squared Ti cubed, Ti star cubed. So we have minus 2 plus 4 times alpha, correct, times dx times T star cubed. Okay, and then the first entry for D is 1, and the last entry for D is also 1. Oops. Right? So we just created this diagonal. Nathan? Pardon me? Yes. Yes. Well, no, this is fine because I don't have mp.1s. So T star is an array, so it's going to make D an array, right? You see it? If I had multiplied it by mp.1s, but yeah, so just to clarify, what essentially Nathan is saying, like, yeah, so we're just make sure that D is actually just this one-dimensional array of size n. And it is, because all of those are just constant values multiplied by an array of size n. So it's going to create an array of size n, one-dimensional array of size n. So this D is going to contain all of these values with this initial T star. Remember, your T star, your initial guess, is an array because at every point you have a different T star in principle. We just made them all equal, but you could have a function for your initial guess. Okay. For example, if you think the temperature distribution is going to be parabolic, maybe create an initial guess that's parabolic. Okay. If your solution is going to be parabolic, start with a parabolic initial guess. You might be closer to drive the entire solution closer to the answer. Okay. Same thing for the right-hand side is minus alpha. Remember, times d, alpha. Sometimes using the Greek notation is painful because you have to put the backslash alpha and then press tab. Dx squared, okay, times, let's see, 3 times T star to the power 4, right? 3 times T star to the power 4 plus T infinity to the power 4. Okay. This is the entire right-hand side. So for this entry is going to contain T2 star. For this entry is going to contain T3 star. That's going to matter. It's important that you put the full array of T star here because T star is going to be different at every point. Our new guess, our new T star is going to be equal to the previous solution, to the previous answer for T. So it's going to be different at every point. So it's very important that you put in this T star over here, this array of T star. So same thing for RHS 0, it's T left, and RHS at the last point is T right. Okay. Now we can build the full system of equations. MP dot diagonal for the lower diagonal, -1, plus MP dot diagonal for the main diagonal D, and plus MP dot diagonal for the upper diagonal at 1. Okay, +1. Now we can solve this. Solution is equal MP dot lin algebra dot solve. A, right-hand side. Maxime? Why not? Why? T infinity is a fixed value for the entire problem. Pardon me? No, it's a scalar added to an NumPy array. It will add the scalar to every entry in the array. Okay. Excuse me? Yes, yes. Thanks, Jake. Right. Okay. So now we solved this problem using this T star. Now we need to check what is the difference between our solution and T star. Is it acceptable? Is it below our tolerance or not? Right. That's the critical aspect that we're doing here. If this were a linear problem, you wouldn't have this while loop because you don't have a nonlinear right-hand side. You just have do this once. Okay. But because we have the nonlinear right-hand side, we had to linearize it. And now with a guess, and then we improve the guess until the guess is equal to the solution. So now we compute an error, which is numpy.linalgebra.norm, which is the norm of the difference between solution and T star, right? I'm going to take an L2 norm. Okay. Now this automatically, this while loop is going to automatically, once it finishes the last line here, it goes in and checks if error is greater than tolerance, repeat. If not, then exit. But I need to do one more thing now. I need to reset my guess to make it equal to the solution. Okay. So I'm going to improve my guess now. I'm going to say T star is equal to sol. Okay. And then that's it. Then I'm gonna print final tolerance is equal, let's say, to the error, right? And then plt.plot x solution, and then plt.grid. All right, moment of truth. Let's make the tolerance a little, a little higher. Make it 10. It doesn't crash miserably. Yay! Look at that. Awesome. It works. Works for me at least. What about you? Yeah. All right, now change things, temperature, etc., alpha, and run it. This is a very highly nonlinear problem. Okay. We got an error over here. Yeah, you have a very high alpha, right, Ryan? Yeah. There you go. Yay. Okay. Beautiful. Beautiful. Okay. So now let's kind of drill down and see a little bit how T star is changing. Okay. So I'm gonna do this for like 15 points so that we can see this a little bit, and just do this for a fixed number of iterations, or maybe just keep it, maybe increase the tolerance a little bit. Okay. And I'm gonna go ahead and print T star. Okay. Print T star, and then okay, T star. Okay, and then also print. Okay, so look, initially we started with T star equal 300 everywhere. The next iteration, the left-hand side stayed at 300. That's the boundary condition. The right-hand side stayed at 500. Went up to 500 immediately. But then look at the intermediate points, right? They changed significantly. And now they started getting closer and closer. They started changing until they kind of stopped changing much. Okay, so let's reduce the tolerance a little bit. You see? Then they're not changing much anymore. 506, 499, 499, we're done. Okay. So in other words, another way of saying it is that your guess is no longer changing from iteration to iteration, or it's just gotten close enough to the true solution. Okay. So you need to know how to do this for the exam. Like, I mean, I can come up with 1,000 problems, right? And you can come up with 1,000 problems, and still I could not cover all cases. Okay. So maybe just do d2u by dx squared equals sine u and try it out. d2u by dx squared equal log u times x squared. Okay, that's a nonlinear right-hand side. Should be able to linearize it and create a system of equations like this and solve it. Okay. How hard was this? I don't think it was that hard. Once you linearize, once you kind of get over that concept of the U star and the T star, it becomes easy. And I feel now, it just occurred to me, like, why don't I do this for the nonlinear system of equations that we described? Having that Jacobian, et cetera, was so kind of convoluted and nightmarish. I mean, we could probably describe it in a way that kind of embeds it like this, without having to talk about the scary Jacobian, etc. And that's it, my pupils.
Can you scroll up to your code?
I can scroll up to my code, please.
Thank you.
Okay. Okay. You guys on Zoom, you're right. Can you see everything? Okay. So the plan for, I'm gonna let you go now. The plan for next week, so your course evaluations have already been sent out to you. If you fill those out, that's great. But I'm gonna give you credit for filling out a course evaluation. So I'm gonna create an anonymous quiz, okay, where you go and describe your sentiment about the course, however you feel about the course in an anonymous way. And I'd like you to upload like a screenshot of your course evaluation, and you'll get credit as essentially as a free quiz. I always get 100% evaluation rates, which is gonna top in the college. So I like that. Like, it doesn't cost me anything to give you an extra 5 points, out of 5%. So it's not, I mean, I guess 96% is my response rate because, there's some who just don't want to do that, and that's fine. So if you already did that, make sure you'll get a chance to upload that screenshot. But next Tuesday, we'll do that in class together. So we'll, or I can just start the quiz. I don't know, maybe it's gonna, yeah, it's maybe easier for you to evaluate. I mean, do you prefer to do the evaluation at home, or like, I can step out of the class? I mean, like, if you feel like, my presence is gonna affect your, like, I'm standing here with like, cute eyes, and I'm like, hey, looking at you. And if you think that's gonna impair your judgment, I'll step out of the classroom. I think I did that last year. So let's do that. We'll do it in class. And then there's a little activity that I do every year with my students. This year I have failed to, I usually get you guys candy for every exam so that you feel better about the exam, but twice this year I forgot, and like I bought the candy, but I think what happened, my son went and misplaced them, and in the morning, and by misplaced them mean put them in his belly, and so and so I didn't see them in the morning, so I didn't bring them with me. But I'll get some next Tuesday and on the final exam to make it up to you with a little piece of candy. But do come on Tuesday. There's a fun activity that I do every year with my students. Those who are taking the class again know what that is, and kind of they're getting bored with it. But we'll get a chance to interact in a very informal fashion, and chat about things and kind of ask questions. And student hours are still the same next week. And I think for Thursday's session, I will also holds will not have class, but I'll do student hours as well. And prep for the exam, and I'll be available as much as possible with a faster response rate with email communication, etc. So I'll talk about that on Tuesday, but please try to come on Tuesday. It'll be fun. We'll make it a nice closure for the semester, and and thank you so much. Okay, feel like, yeah, Michael. So yeah, I'll do the same kind of thing for a study guide and the review slides. Yeah, I'll put those up on Canvas, just like for every exam. Yeah, Jake. Let me pause the recording. Okay, on Zoom, I'm gonna pause the recording. You're welcome to